First, what are the strategies to register this? Because we can both utilize a strategy for single view, and we can utilize a strategy for using the point clouds. And then second, we're going to talk about some of the options to detect the correspondences. So option one for registration, similar to single view. You have the BIM, we take the image from the BIM, you have one of the images there. The same rules as for FIM complexities still apply here, meaning that you can only utilize the elements and the points on those elements and the correspondences if you have certainty that these two comply, meaning the first level. If they don't comply, then you need some sort of external check, right? You need some sort of, let's say, control point between the BIM and known in your particular image as well, in order to perform the corresponding pixels between the image of the BIM and the reality of your image. From that, you match these two together, and then you find the relative orientation between them. The second part is to find at least three non-collinear point correspondences between your BIM and your point cloud this time. This is to perform the similarity transform, meaning to perform the rotation, the translation, and the scale. So level 1 FIM, elements can be used. This is where you can utilize, let's say, the corners of these. Similarly here and similarly here, we find 3 of these points. We perform the similarity transform. We can use the horns method that I discussed before. Level 2 FIM. This time we can't use these because we cannot guarantee that these are the same. And if we cannot guarantee it, there's no use to us to say that these two comply together if we don't have any verified check and if we don't have any ideas. And more importantly, if we're actually checking that. Because if we're actually checking that these are compliant or not, in terms of its position, in terms of its size, all of these aspects, now we're taking all of these points and we're making sure that they comply. And that is what's inaccurate about it. So we need, again, at least 3 non-collinear points. We can either have these, we can have QR codes, we can have, but the most common is the circular or spherical targets, or these types of targets as well, that are in control points with known locations. So you have the manual method. That's going to be essentially the BIM and the point clouds that are separated from each other. And then we want to get from here onto here, right? So one way is to have some target-based registration, right? So you have some targets. Using these targets, as long as 3 of them that are non-collinear, you would be able to register the 2 models together. So the prerequisite of this is that I need to know the center of these in my scan of at least 3 of these, and I need to know the exact center of these in the model as well. And that's not hard because we actually build the grid of the site based on that. So there are what we call some control points. So we can get that information. It's just that it's not as effective to want to do it every time. It's much easier for us to basically have a scan and be able to extract the information that we want directly from it. So I have a method that I used particularly for a particular type of problem, which is our rectilinear problem, which is actually the majority of our building constructions look like this, right? Even this building, you would be able to do this. What does this mean? That means that the majority of the points that we extract are in 3 orthogonal axes. And then from that, that's what I call rectilinear for building construction. What does that mean? That means that our normal vector for our floor is in this direction. Our 2, walls are also orthogonal together. So if we get the majority of the points related to these, and we get the normal vectors of the points around each and every one of these points, what is it going to give us? It's going to give us the 3 main orthogonal axes. Make sense? Yeah. So what I do is I basically get the normal vector associated with each and every one of the points. I find the free normal vectors from all of the normal vectors of the points that are the most frequent and are pairwise orthogonal or close to orthogonal. And in order to do that, I basically introduce it as a quadratic unconstrained binary optimization to be able to get that information. Okay? Once I do the rotation, then I go and I use a particle swarm optimization or any type of AI-based optimization to basically come and shift it in each and every one of these three directions. Because once I rotated it correctly, what does it give me? It gives me the correct rotation and orientation. Now the only thing that is left in this direction, I have to move it and it locks somewhere. In this direction, I have to move it and it locks somewhere, and then in the up-down direction, right? So I do it 3 separate times for x, and this is a thorough objective function that is necessary in order to do this. Once you do that, you basically get the result. And this is an app that I developed for you guys so that you can have a demonstration of it as well. So terrestrial laser scanner point clouds. If you take a look at the floor objects here, and you look at the histogram, you're going to see something like that. If you take a look at the peak of the histogram itself, it's around 3 millimeters there, which is consistent with the amount of random measurement error that you get in the instrument. BLK2GO, this one I got it from the Leica website. This one, if you take a look at it, is 5 millimeters. So a bit more. The fact that it's 5 millimeters is more or less consistent with reality. You know, we're not expecting the handheld laser scanner that is mobile to actually be as accurate as your terrestrial laser scanner, right? Fast forward to if I wanted to do it with an iPhone X, and this is more consistent with what it is. You have different types of peaks. Why do you have these? Because every time that it's doing the stitching, there's some errors associated with that, right? So it is having those errors as well. And if you take a look at it, this is around 2 centimeters. So how do we incorporate uncertainty? Well, there are some measures that you would be able to do, and we call it error ellipsoid. What does this mean? This means that for every point, there's an uncertainty associated with it that comes from various sources. That uncertainty that is associated with that particular point comes from the random measurement error, okay? It comes from registration error, and it comes from various different other aspects as well. That is going to be the sigma in the middle that you're going to be observing here. That's what we call the covariance matrix. That covariance matrix would tell us how large this ellipsoid is going to be, right? In this direction, or in this direction, or in what direction? Is it a sphere? Is it an ellipse? What is it? Ellipsoid, what is it, right? That's what that covariance matrix is going to provide. And then the xi is basically your center. So for every point, you're basically going to be getting that there, right? From that area. And then that would be the center. And then it gets enlarged there. And then here, you have a probability there. That is the chi-square distribution with probability P and degree of freedom alpha. Degree of freedom is basically the dimensions of your data. In this case, it's 3-dimensional, so the alpha is going to be 3. P is going to be your confidence level. So it's going to be 95%, 97.5%. What is going to be the confidence that you're going to want? That would be dictating exactly how much the semi-major and the semi-minor axes are going to be. So the directions of these would be provided by the eigenvalue analysis of the covariance matrix. This is exactly, if you remember, our principal component analysis. The lengths of these would be determined by means of our chi-square distribution. From that, we know more or less how much, dependent upon the standard deviations that we have from each and every one of the areas, how large this error ellipsoid is going to be with respect to a particular amount of probability. If we want 95% probability is, let's say, this much, 97% is a bit larger. That means that it would encompass all points that are randomly sampled from a multivariate normal distribution with standard deviation, with covariance sigma and mean of xi. That's what this means. Once we have these ellipsoids, then we would be able to see whether that particular surface is within that ellipsoid as well or not. So let's say if I want to say there's a correspondence between a point and a surface, that point could be anywhere inside of this ellipsoid. Then if these two are going to collide or have some sort of intersection, we can say that this point has some probability of intersecting with this surface. As long as they intersect, we can say that they belong together. Same with a cylindrical surface or a curved surface, it's going to be the same. It doesn't matter. As long as that surface intersects with that particular error ellipsoid, there is a possibility that is going to be inside of it. So the first way is to do an ICP similar to what you guys have done, and you guys know how it is. So we build a point cloud 1, which is the point cloud of our digital model. We have a point cloud that we collected from the same elements. These two have no dimensional mismatches, so we know that they have correspondences. The only thing that is left here is to refine our registration from whatever initial registration we had to make sure that we get the best amount of correspondence between the points in the model and the point cloud. So these are registered, target-based, or using my method, however way it is, depends on the type of problem. From this, we have to find the distance, so they are already close together, right? We are not assuming that they're way far away, and I'll give you an example of why that is extremely important. If it's between a particular distance, this distance fresh, which we showed the other there, if it's 5 centimeters, it wasn't that good. If it's 12 centimeters, better. Once we do that, we find all of the points that are closer than this distance threshold. Once that there is, we find these points, get the correspondences, do a rigid body transformation, get the rotation and orientation. Now we have a new, basically, point cloud that is registered together with this model. Then we do it again and again and again and again until the RMSE is smaller than a particular threshold. That's where we stop. So if it's larger than a particular threshold, that's where we continue. However, normally this is very subjective to want to do it that way because we don't know how much the RMSE is supposed to be a priori, right? It's very, very hard to be able to say, okay, 10 to the power of minus 5. You know, that's unrealistic. However, we can emulate convergence by saying between every 2 iterations, our RMSE is not going to be changing more than, let's say, 10 to the power of minus 5, 10 to the power of minus 6, right? If we can do something like that, then we have the opportunity to be able to estimate our convergence properly. Make sense? That means that between 2 different iterations, our RMSE is not changing significantly. And if it does not change significantly, that means that it is an indication of convergence. The other one is a plane-based registration, which basically I talked about in my paper. And this way, as long as you have each and every one of the planes that are associated with each and every one of these surfaces, that would make it extremely easy for us to perform a plane-based registration between those points. And this way, instead of us having a plane-based registration with respect to planar surfaces, we actually get all of those points, assume that they are a planar surface, and then we register the point to the plane directly, not point to point. That is significantly better, faster to converge, and it's more accurate, actually. Until no additional point is smaller than our basically threshold that exists there with respect to the standard deviation that we had, which comes from the error ellipsoid. This way, we are actually estimating it through the error ellipsoid directly, and we're not just having a random, let's say, subjective cutoff for our convergence. It might converge a bit later, but in theory, but in practice, it actually converged quite easily, quite faster.